Next, we'll talk about Gaussian mixture model. So far, we have talked about two clustering algorithms, k-means and hierarchical clustering. They are both hard clustering method, which means every data points only belong to a single cluster. And Gaussian mixture model is a soft clustering method.
Soft?
Yes, soft clustering. So every data points can belong to multiple clusters with a different degree. So first, what is a Gaussian? Gaussian distribution is the most popular continuous probability distribution. It is also known as the normal distribution. The shape of Gaussian is a bell curve like this. And Gaussian distribution has two parameters, mu and sigma. And the mu variable corresponding to the center of the bell curve, and the variance sigma captures the spread of this bell curve. When the variance is small, the spread will be small, which means all the probability will be concentrated around the mean. When the variance is large, the probability will be scattered, which means the events that are far away from the mean can still happen with a large probability. Now let's introduce the mathematical definition of Gaussian mixture model. The probability of a data point x is the weighted sum over k Gaussian distribution. Here, the pi k is the mixing coefficient for cluster k. Intuitively, it tells us how big the cluster k is. And mu k is the mean of cluster k, or the cluster center for cluster k. And sigma k is the covariance for cluster k. So here's an example when we have a two Gaussian distribution. And data points x will be generated from these two underlying Gaussians. For a Gaussian mixture model, the goal is to figure out the parameters of the two underlying Gaussians, namely finding out pi k, mu k, and sigma k, given all the observed data points. To compute the Gaussian mixture model, we utilize a popular optimization strategy called expectation maximization, or EM algorithm. Next, let's see how EM algorithm works for a Gaussian mixture model. We first initialize all the parameters for Gaussian mixture model, include mixing coefficient pi k, the center mu k, and variance sigma k. Then in the E step, we assign each data points xn with the score gamma nk for each cluster k. So in this case, data points xn will have k scores, one for each cluster. In particular, gamma nk tells us how likely xn is generated from cluster k. Once we have all the assignments, then in the M steps, we update all those model parameters, pi k, mu k, sigma k, using the scores we have learned from those assignments. Then we check if convergence criteria are met. For example, likelihood is no longer changing or parameters are stabilized. If no, we continue this EM iterations until convergence. If yes, we return all the model parameters for Gaussian mixture model. Next, let's look at those steps in more details. In order to run EM algorithms for Gaussian mixture model, we have to initialize all those parameters. In particular, we have to find the mixing coefficients, the centers, and variance for each clusters. And this initialization step is very important. A bad initialization can cause many subsequent iterations until convergence. A good initialization can save a lot of iteration so that the convergence can happen very quickly. For example, in this picture, if we initialize these two clusters here and here as a center, and also give an equal weight for the mixing coefficients, this will be a pretty bad initialization because the starting point of this two cluster center do not coincide with any data points, which means subsequently the EM algorithm has to iterate many times to correct this bad initialization. So what will be a better initialization? we can actually use k-means result to initialize for Gaussian mixture model. For example, the centers in the Gaussian mixture model will be the center from k-means result. The covariance matrix sigma k can be computed by using all the data points from the corresponding clusters. And finally, the mixing coefficient pi k can be simply computed as the size of the cluster k divided by the total number of data points. And usually, this initialization with k-means result will be much better than a random initialization like this. Next, let's talk about the E step. In this step, we'll assign each data point a score gamma nk for each cluster k. And the gamma nk can be calculated with this equation. And the numerator has two terms, pi k, the mixing coefficient for cluster k, the probability of xn in cluster k. And the denominator is to normalize this assignment score to between 0 and 1. For example, we have one blue Gaussian over here and one orange Gaussian over here. The assignment score for this point is 0.5 for the blue Gaussian and 0.5 for the orange Gaussian, which means this point is equally likely to belong to the blue cluster or the orange cluster. The assignment score for this point is 0.8 for blue Gaussian and 0.2 for orange Gaussian, which means this point is more likely to come from this blue cluster. And the E step is to going through all these data points by assigning all these assignment scores. Now let's talk about M step of Gaussian mixture model. In this step, we'll update all the model parameter pi k, mu k, sigma k using all the assignment score we have learned from the E step for each cluster k. First, let's define an auxiliary term nk, which equals the sum of all gamma nk for a specific k. And intuitively, nk is the size of cluster k. Then we calculate mu k equals the weighted sum of all the data points in cluster k divided by nk, the size of cluster k. Intuitively, mu k is the center for cluster k. Then the covariance sigma k can be computed with this equation. This particular term corresponding to the covariance from data points xn. Intuitively, sigma k is the covariance of all data points in cluster k. And finally, the mixing coefficient pi k is proportional to the size of the cluster nk. In other words, pi k is a prior probability for data points to belong to cluster k. Now let's visually illustrate how Gaussian mixture model works. The goal is to run Gaussian mixture model over this set of points. We first initialize two Gaussians indicated by the blue and red circles. Then we compute assignment scores for each data point. The bluer points indicate the assignment score for the blue cluster are higher. Likewise, the redder points indicate the assignment score for the red cluster are higher. Then we update the Gaussian mixture model's parameters based on the new assignment scores. In particular, we update mu, sigma, and pi. Then we iterate the E step and M steps until converges. And here are the final result of Gaussian mixture model after 20 iterations. Now let's compare two clustering methods, k-means and Gaussian mixture model. In terms of clustering algorithm itself, k-mean is a hard clustering algorithm. Each data points only belong to one cluster. Gaussian mixture is a soft clustering algorithm. Each data point can belong to multiple clusters with different weights. For k-means, the only parameter is the center, mu k, for each cluster. But for Gaussian mixture, we have three parameters. In addition to the center mu k, we also have mixing coefficient pi k and covariance sigma k. Both k-means and Gaussian mixture model utilize EM algorithms, where they iteratively update the clustering assignment and model parameters.